start the lecture for topic 7. Okay, so the first part of the topic 7, part 1. So today we will do part 1, first part of topic 7. Okay, before we start topic 7, let's start the reviewing topic 6, the second part, the last lecture of about the topic 6. So we in the last lecture we talk about bivariate distribution. So bivariate distribution is what? So we have two random variables x and y, right? Two random variables x and y, and we talk about bivariate distribution, which is a joint probability distribution. Probability of x equals to small x, y equals to small y. And when we talk about this joint distribution, we can also naturally talk about the covariance and correlation. So covariance between two random variables and correlation between two random variables, right? Sigma xy and rho xy, right? And then we talk about typical, discrete random variable and their distributions. So Bernoulli random variable and Bernoulli distribution, which was not in the lecture note, but this is very simple distribution we always have talk about, right? Tossing a coin, so yi equals to 1 with probability p, yi equals to 0 with the probability 1 minus p, success and failure, right? So we can rewrite this probability as a p to the y, 1 minus p to the 1 minus y. And then if you sum them up, this yi, if you do this trial n times, right? This Bernoulli trial n times, and we count the number of successes, then that is basically summation of yi I equals 1 to n. That is the number of successes in the n Bernoulli trials, which is a binomial experiment, right? Binomial experiment, you count the number of successes, then that x is a binomial random variable with n successes, n trials, and p is a probability of success, and this x is the number of successes, right? Number of successes. And probability of x equals to small x is n choose x, p to the x, 1 minus p to the n minus x, and x can be any number between 0 to n, any natural numbers. And expected value of x is m times p, variance of x is np, np 1 minus p, okay? And Poisson random variable, if you have an interval, which is a length of time or length of the area or size of the area, and how many successes it happens during the length of time or during the pages or spaces within the space, a particular length of the interval, then this probability of x is small x, small m number, x is a number of successes, and that is e to the minus mu, mu to the x, and x factorial. This is basically how the distribution look like, and this is discrete probability distribution for x equals to 0, 1, 2, and expected value of x is mu, and variance of x is also mu. That is the Poisson random variable. And this example, we solve some example questions, exercise questions. Now we will move on to topic 7. This topic 7 is what about? Is about the continuous random variables. Okay, continuous random variables. Okay. So continuous probability distribution and continuous random variables, Keller's chapter 8, Doan and Sewell chapter 7. Okay, so probability density function, cumulative distribution function, uniform distribution, normal distribution, exponential distribution, and other continuous distributions. Up to here, our midterm exam will cover up to here. Midterm covers up to here. Okay, up to the exponential distribution. Okay. Unlike a discrete random variable, which we studied in the previous topic, a continuous random variable is one that assumes an uncountable number of values. So x can take any values, for example, between minus infinity to infinity, or x can be any number between 0 and 1, something like this, any number. Okay, x can be any number between minus infinity and infinity, or 0 and 1, or inclusively 0 and 1, something like this. It doesn't matter whether 0 is included or not, 1 is included or not. We cannot list all possible values because there is an infinite number of values, right? It can be any number between 0 and 1. So 0 can be any value, 0.0000001, 0.0000001, and There are infinite number of values, right? Because there is an infinite number of values, the probability of each individual value is virtually 0. Because when we calculate the probability, then this 분모, this denominator is how many values can be possible. And then it's 1 over how many values possible. Then there is basically infinity in the denominator. So the probability of x is small x when x is a continuous random variable is always 0. Okay, when x is continuous random variable, probability of x is small x is always 0. This is very important feature of the continuous random variable. Instead, we can determine the probability for a range of values. So probability of x equals small x, we cannot do this. So instead, we may want to do probability of x is between a and b, something like this. Okay, so then that is what we want to calculate with a continuous random variable. With a discrete random variable, when we toss a die, it's meaningful to talk about probability of x equals 5. But now you think about the die with the infinite faces. 주사위가 있는데 주사위의 면이 무한히 많은 거예요. If you draw that faces, then probability of x equals 5 is basically 0. There are infinite number of possible values, and among those infinite number of possible values, one value is realized, that probability is always 0. Okay. So in a continuous setting, with a time as, for example, the range of a random variable, then probability the random variable interest takes exactly 5 minutes is infinitesimally small, which is basically 0. For example, like you are waiting for of your friend, and your friend arrive exactly in 5 minutes. That probability is 0. That your friend may arrive in 5 minutes 0.00001 second, or 5 minutes 0.0002 second, or so on. The person cannot exactly arrive in 5 minutes. Okay. So instead of probability of x equals 5, we talk about probability of x is less than equal to 5, or probability of x is less than equal to 5, or greater than equal to 5, something like this. We talk about the range of values of x, and we talk about probability for those ranges. Okay, and probabilities are defined now as the area, as an areas under a curve that is called the probability density function, which is called PDF. Okay, PDF is a very common term these days, but probability density function is also known as a PDF. Okay, and the function f of x, small f of x, 소문자 f of x is called probability density function, or PDF, of a continuous random variable x. Or you can write down, if we want to emphasize that this is a x's probability density function, then you can use this subscript x after this f, right? F of x over the range of the values a and b. This means what? This means at this point you have to be careful. This is the range of the value that capital X can take. So x or small x can take values this small x, right? Small x, and this small x can be only between a and b. Okay, cannot be below a, cannot be above b. Okay, 한번 다시 설명합니다. Let me repeat this in Korean. 캐피탈 X라는 랜덤 베리어블이 A하고 B 사이의 값만 가질 수 있다. 그렇죠? A보다 작을 수 없고요. B보다 클 수 없을 때를 지금 가정하는 겁니다. Okay, so capital X can be realized with small x, and small x is always between A and B. In this case, between A and B, always this probability density function must be greater than equal to 0. So that is the condition for the PDF. Condition for the PDF or PDF. PDF has those 4 conditions. PDF must be always greater than equal to 0 within the range that X can take. Okay, X can take. And the total area under the curve below this A and B must be 1. Okay, so here this is f of x, this is f of x is here. Okay, f of x, this is f of x, and this area must be 1. Okay, this area must be 1, 넓이 must be 1, and mean, variance, and the shape depends on PDF parameters. PDF parameter we will see in a few slides. So PDF parameter will determine mean, variance, and the shape of this PDF graph curve, and PDF reveals the shape of the distribution. But this number, for example, this number is not the probability. This is not the probability. This is f of x, which is not equal to probability. Okay, it's not probability. Okay, it's not probability. That is the important thing. This curve, the area under the curve is actually the probability. For example, you look at this area, and say this is a 1 and this is 2, and this area is probability of 1, x is between 1 and 2, and this area is probability. But this number is not probability is x equals 1. This number is not equal to probability of x equals 2. No. Okay. And there is another function which is called capital f of x. Capital f of x is called a cumulative distribution function, CDF. CDF of a continuous random variable x, and this f of x is equal to probability of this random variable x is equal less than or equal to small x. Okay, this is f of x, capital F of x, which is a cumulative proportion of scores, and this is useful for finding probabilities. And an example of a CDF for a normal random variable, normal distribution, is shown in below. So this is a normal CDF. Normal CDF is going up. So probability of x is less than or equal to x will goes to 1. If x goes to infinity, then this probability must be 1, right? Probability of x is less than infinity is always 1, right? Okay. And probability of x is less than minus infinity is 0, right? So probability is start from 0 to 1. Okay, 1. Start from 0 to 1. And that's the cumulative distribution function. Okay, you may think, oh wow, now we have too many new things. One is the probability density function, and the other one is cumulative distribution function. But actually, probability density function and probability distribution function, their relationship is this. So probability density function is this. Then this, if you look at this point here, if you pick a point here, this is say x, then this area is probability of x is less than x, right? And this is capital F of x, CDF. Okay, CDF is the area. PDF is what? PDF is this point. This point is f of x. Okay, and this area is capital F of x. So capital F of x will show the cumulative probabilities, probability up to the a to the x up to minus infinity to the x, and this f of x shows the value of this graph. Okay, and this graph is not actually the probabilities. Okay. And probability is an area. So so continuous random variable has their PDF and CDF. Unlike discrete distributions, the probability of at single point, probability at single point is always 0. So probability of x is small x is always 0. And the entire area under any PDF is set to 1. Okay, so that is important. So if this is a PDF, then the area under this curve, all area under this curve must be 1. Okay, and area under the curve between any number between a and b, or you can say c and d, or c here and d here, then this area is probability of c, x, c, d, and this area is probability c, x, d. Okay, so area on a and b here, and this is the PDF. Okay, then this area is probability of x is between a and b. Okay, here now x can take any number between minus infinity to infinity. Then probability of a and b between a and b, x is between a and b, is this area. Okay, so that is the PDF, what PDF give us. Okay, in the previous topic, in topic 6, we introduced the discrete random variable. Let's think about discrete random variable. Discrete random variable x has a probability distribution which is x equal to small x. Okay, x take finite values, and there is a probability of x equal to small x. If x is 0, 1, 2, then probability of x equals to 0, probability of x equals to 1, probability of x equals to 2. And then what we have done, after this, what we have done was expected value of x, which is summation all x times probability of capital X is small x, right? That was expectation of x. And we also calculated the variance of x, right? That was what we have done in the discrete case. Now we want to calculate the expected value of x based on this PDF, okay, PDF, which is f of x. Using this f of x, can we calculate the expected value like this? That is what we want to do. Okay, so we want to find the formula for expected value of x, which is a counterpart of this discrete case, using this PDF that is shown in the next slide. Okay, the mean and the variance of a continuous random variable are analogous to expected value of an x and variance of x for discrete random variable, except that we replace this summation sign with the integral sign. Okay, so continuous random variable x, discrete random variable x. Discrete random variable x, expected value of x was what? Summation all x, x times probability of x equal to x. Continuous random variable, expected value of x is now x is still here, and instead of summation we have integral fx dx. Okay, so integral fx dx. So this part minus infinity to infinity. This part is basically the expected value part, and here the sx is here. Okay, so this is the expected value of x. Okay, expected value of x. Variance the same. Now we have this integral fx dx, and here we have x minus mu squared. Okay, expected value x minus mu squared. This is here, right? And expected value is here. Okay, so variance and expectation is basically the integral instead of summation. Okay. Next, let's move on to typical distributions. I think once we look at these typical distributions, then what we have discussed in terms of the concepts will be more kind of obvious. Okay, so there are a few typical probability density functions, and the most popular one is a normal probability density function. Now, before we talk about normal, we talk about uniform probability distribution. Uniform is what? Same for everyone. Okay, same. So probability is basically the same. Okay, so let x be a uniform random variable that takes values x between a and b. Okay, a is between a and b. Then probability density function is just a flat. Okay, there is a x, and x can take value between a and b, and here the probability density function is just a flat. Okay, in this area, in this a and b range, the probability density function is flat. Okay, now this is f of x, probability density function. Now think about it. X, this capital X, can take values between a and b, right? A and b. And then this probability below, probability of a, x is between a and b, must be 1, because x can take only value between a and b. And then this probability uniform distribution is same, exactly same, the flat line within this A and B, then this area must be 1. Okay, this area must be 1. Area must be 1. Okay, area must be 1. And then this 밑변, 3번, this segment is B minus A, right? This segment is B minus A. And this height is basically the f of x, right? This height. But this area must be 1, then this height must be what? 1 over b minus a, right? So if x is a uniform random variable between a and b, then f of x is b minus a, 1 over b minus a x, b. Okay, that is basically the uniform random variable, and it's PDF. So uniform PDF is basically 1 over b minus a, and this area, that will make this area 1. Okay, 1. Okay, that is the uniform random variable. How about probability of this point is say x? Okay, then how about probability of x is less than x? Okay, less than x. That is this area, right? This area. And this point is what? This 밑변, this segment is x minus a. This base or 밑변 is x minus a, right? X minus a. And 높이, height is b minus a over 1. So b minus a over, so this 밑변 is, I should have write down x minus a is a 밑변, and height is b minus a, or 1 over b minus a. So probability of x is less than x, this area is what? This area is x minus a times 1 over b minus a, 높이 and 밑변, right? And base and height. Okay, so x minus a times 높이, height, 1 over b minus a. So probability of x is less than x is b minus a, x minus a over b minus a. Okay, and a x b. Okay, so this is x minus a over b minus a x b. Why I have calculated this? Why do you think I have calculated this? Because this is what? This is probability of x equals to small x, which is cumulative distribution function, CDF. Okay, so uniform random variable PDF is b minus a, 1 over b minus a. CDF is x minus a over b minus a. Okay, x minus a over b minus a. So x minus a over b minus a is here. Mean is a plus b divided by 2. Variance is b minus a squared divided by 12. You need to actually calculate the this is a integral minus infinity to infinity x fx dx, which is a to the b x b minus a over 1 over b minus a dx. But you don't have to calculate this like this. You don't have to do this. If a is here and b is here, okay, then this is the f of x, right? F of x. And actually the mean is the middle point. This middle point, this is the mean expected value of x, which is a plus b divided by 2. Okay, this middle point is actually a plus b divided by 2. Variance you have to calculate using this a to the b, x minus mu square fx dx. We don't have to calculate. I'm not going to calculate. I'm not going to do any integral in this course. But you may want to memorize this variance, which is b minus a squared divided by 12. And the relationship between PDF and CDF. So PDF is basically what? PDF is f of x, right? And CDF is a capital F of x. Capital F of x is probability of x is less than equal to x, which is 적분. You are basically doing 적분. This you are basically calculating this area, right? This area. And this area, calculating this area is basically using the integral minus infinity to the x f of v dv, and where f of v is the PDF of capital X. Okay, so this is the just a note. The cumulative distribution function and probability density function has this integral relationship with each other. So actually, f of x is f of integral. The derivative of x. Okay, first derivative of x, f of x, capital F. First derivative of capital F of x is small f of x. Okay, 미분, 적분. Okay. Let's try to solve an exercise question. So the amount of gasoline sold daily at a service station is uniformly distributed with a minimum of 2,000 gallons and a maximum of 5,000 gallons. So in this short two line, there are many informations that we can transform into statistical language. So first thing is given is the amount of gasoline sold daily at a service station. This is a random variable. Which we will call x. X is the amount of gasoline sold daily at a service station. And it says it's uniformly distributed. So let me use this notation. X is tilde, uniform. The x is distributed uniform, and between 2,000 and 5,000. So I will say 2,000 and 5,000. And this is A and this is B. Okay. Then this will give us probability f of x is what? B minus A, 1 over B minus A, that is 5,000 minus 2,000 in the denominator and 1 in the numerator. So 2,000 x 5,000. Okay, so that is f of x. Then what about the cumulative distribution function? Cumulative distribution function is what? X minus A divided by B minus A, which is x minus 2,000 divided by 5,000 minus 2,000. 3,000 3,000 in the denominator and x minus 2,000 in the numerator. Again, x is between 2,000 and 5,000. Okay. So we can use this information to calculate the part A. What is the probability that daily sales will fall between 2,500 and 3,000? So probability of 2,500 x 3,000, which is what? Probability of x is less than 3,000 minus probability of x is less than or equal to less than 2,500. By the way, it doesn't matter whether you put equal sign to here or not. Why? Because probability of x equal to 2,500 is 0. So we can just put this equal sign here. Then this is f of 3,000 minus f of 2,500. You plug in this number to here, then 3,000 divided by 3,000 in the denominator and 3,000 minus 2,000 minus 3,000, 2,500 minus 2,000. And this will give us 3,000. This is 1,000 and this is 500, so 500, which is 1 over 6. Okay. Part B, I think this will leave you a quiz today. Or quiz is part B. That's very simple thing, so you can try by yourself. But let me try to solve part A with a different method, another method to solve the part A. Part A was what? between 2,500 and 3,000. So we can draw a picture of this graph. So x is a random variable which takes value between 2,000 and 500. So there is a 2,000 here, okay, and 5,000 here, okay, and then there's a flat line, uniform random variable, flat line, and this is gonna be what? This area must be 1, and the base is 3,000. So this must be 1 over 3,000. Okay, so 1 over 3,000. Okay, and this is basically f of x, right? This is f of x. And then this question asks, first question is between 2,500 and 3,000. So you may pick this point. This is what, 2,500, and this point, this is 3,000. And this is PDF, right? PDF. And under the curve, under the PDF curve is the probability. And this area is probability of x is between 2,500 and 3,000. Okay? And this area, even if we don't know how to calculate the CDF, we don't need to calculate the CDF. We only need to calculate this area. Okay, this area, you can calculate this area as a base, which is 500 times the height, 1 over 3,000, which is 1 over 6. Or even you don't need to calculate this as a base and the height. One way you can calculate this is just look at this segment, look at this base. The length is what? 3,000, right? Length is 3,000. And all this graph is always uniform, right? Uniformly the same. Then this base is 3,000, and you calculate the probability for this part. This part is 500. This length that you are interested in is 500, right? Among these 3,000, we are interested in this part, which is 500 over 3,000, right? So this is gonna be 1 over 6. 500 divided by 3,000, so 1 over 6. So this is how we use the graph to calculate this 1 over 6 instead of using this cumulative distribution function. Part B is a quiz for you guys today. So please solve the quiz for today. Okay. To normal distribution. So normal distribution is the most important of all probability distribution. So among all probability distribution, including discrete and continuous probability distribution, normal distribution is the most important one, okay, in statistics. So the probability density function f of x of a normal random variable capital X is given by this form. The form is actually quite complicated. 1 over square root of 2 pi times sigma and e to the minus 1/2 times x minus mu divided by sigma, the quantity square. And x can take values from minus infinity to plus infinity, right? So in this kind of continuous random variable, maybe the important thing is the formula, the form of the PDF, the mathematical formula. Let me say mathematical mass formula of the PDF fx is the important thing, because this fx shows this kind of graph. This is f of x and this is x, then basically fx is this. If it's the normal distribution, fx is like this. If it's a uniform distribution, then it is like this, right? A and b, right? So x, and this is basically the fx, right? So this is what the continuous random variables PDF looks like. And then the probability is basically the area below this graph, the PDF, so A and B. Then this area is basically probability of A. X is between A and B, right? So this area is the probability of X is between A and B. And if this is A, then this area is probability of x is less than a, and this is by definition the cumulative distribution of a, right? Cumulative distribution evaluated at a, right? So this normal PDF is bell-shaped and symmetric around the mean mu. So mean is here, this point is mean mu, and the distribution is symmetric around this mean value mu, and the bell-shaped, right? Bell-shaped and symmetric distribution, which is the normal distribution, right? So normal is very important, and some people call this normal distribution as a Gaussian distribution. So Gaussian. So some people say, oh, there is a Gaussian distribution, but then don't be intimidated about this Gaussian distribution. This actually is the same as the normal distribution, okay? So this normal distribution is fully defined by two parameters. It's mean and the standard deviation. So when we say x is normally distributed, we use this kind of notation. So x is distributed with mean mu variance sigma square. Do you remember the binomial and Poisson and Bernoulli and the uniform distribution, right? We talk about those distributions. When we say Bernoulli distribution, when x is a Bernoulli distribution, we use this tilde, which is a distributed with this Bernoulli distribution. And Bernoulli distribution, the only one parameter is a p, the success probability. And x is a binomial distribution, binomial distribution, binomial distribution with the two parameters. One is the number of trials and the probability of success. Okay, and x is a Poisson distribution. Poisson distribution has a one parameter, which is mu, right? Mu. Here expectation of x is p. Here expectation of x is n times p. Here expectation of x is mu, and which is the variance of x, right? And you can also think about the variance, how the variance looks like in here. And then x is a uniform a and b, uniformly distributed from a and b. The expected value of x is what? A plus b divided by 2, right? So both these parameters basically fully define the distribution of x, right? So mean and variance. Variance was what? Variance, this is variance, p times 1 minus p, np 1 minus p, right? The variance is what? Variance, you may remember 12 on the denominator and a plus b square or something like this, right? So you can go back to uniform. The variance is p minus a squared divided by 12, right? P minus a divided by 12, right? This is the variance. So these guys are the variance, right? These guys are the variance. And now we have normal distribution. So x is normal with mean mu variance sigma square. So there are two parameters, sigma square, right? And mu is the mean, right? So there are two parameters, mean mu and variance or standard deviation sigma, that is fully defined the normal distribution, the shape of the normal distribution. Okay, and uniform distribution has a range which is between a and b, right? But normal distribution basically has a range which is between minus infinity to plus infinity, right? So minus infinity to plus infinity. Okay, and if we increase, if we have x is a normal distribution with mean mu variance sigma square, when mean is 0 and sigma square is 1, then we will call this as a standard normal, and this guy we especially use Z to denote the normal distribution with mean 0 and variance 1, right? 1 square, which is 1, right? So normal distribution with mean 0, variance 1 is a standard normal distribution. So this is standard normal. So standard normal distribution, which has a mean 0 and variance or standard deviation 1, which is called standard normal distribution. So Z is distributed with the normal with mean 0, variance 1. If you plug in 1 here and 0 here, right? 1, then you will get 1 over square root pi e to the minus 1/2 x square, right? So that is distribution of z, okay? Distribution of z. Okay, and this pi is a pi. The pi, which is 3.1415 ... This is the pi, right? The one from the circle, right? One from the circle. So this is the distribution of z, the standard normal random variable. So f of z is 1 over square root of 2 pi e to the minus z square divided by 2. So z, we use z instead of x for this standard normal random variable. And if we increase the mean, mu goes up, then the curves goes to the right. So this black one has a mean which is 0, mean 0. And if you increase the mean, then the curve goes to the right. So mean is 1, mean is 1, then the blue graph, mean is 2, then the green graph, so it goes to the right. Okay, as we increase the mean, the graph goes to the right. Okay, for the normal distribution. If we increase the standard deviation sigma goes up, then what happens is the graph becomes flattened. Okay, graph becomes flattened. So this blue one has sigma which is 1/2. You increase the sigma to 1, then it becomes flattened. And if sigma becomes 3, then it becomes even more flattened. Why? Sigma is what? Sigma is a standard deviation, right? Standard deviation of x. Sigma square is the variance of x. Variance is big, means the values are more like spread, right? Values become more spread. So sigma goes up, then the PDF is actually being more dispersed, right? Because PDF become more dispersed. Okay. And maybe this is a good point to stop, and I will talk about the second half of the chapter topic 7 in the next lecture. Okay, so let's stop today's lecture here. Okay, today's lecture here. Thank you.